We'll start again. Sorry for the delay. I have to some tea with the big boss, so take some time. Okay. So what I just explained you is this was with last slides that you have here. And I just explained you that there was a maximum of eruption just below, if not at the KT boundary. And well, this warming was probably due to the onset of the Deccan traps, but mainly due to the fact that to the north we have the onset of this event starting before than to the south. So the question now is to know if in some of the section that I just show you, I show you section in Italy, in France, in all these things. There is a problem? No? Okay. So I show you some sections, and we were trying to look for a marker, a benchmark if you want, which may be related to this huge Deccan activity. And since 5 years, there is methods, namely to look for mercury anomaly through volcanism, because mercury generally in the former times is very dependent from volcanism, and the volcanism is really a substantial source of mercury to the atmosphere. And generally mercury is emitted by volcano as gaseous and characterized by longer atmospheric residence times than the other volcanic metals. It's 1 or 2 years. So meaning that mercury can be exposed up to the stratosphere and can travel all around the Earth and be redeposited. So it means that if you have some anomaly, you may correlate this anomaly with some volcanic activity. But there is some exception here. It's always like that. When you create or you find a new methods, and this mercury investigation is quite new, 5 years old, more or less. It's quite simple to analyze. You have a special spectrometer for that, which are not very expensive, a lot less expensive than the one that you are using for stable isotopes, for example. And it's easy to do, but the problem that mercury has some limitation. For example, a lot of people are starting, and it's always the same thing, you know, with the new methods. The 2 first year, you can publish anything because people don't know these methods. You are using the method without knowing really the limitation. And with the years of investigation, you find more and more limitations. The same for the stable isotopes, for example, with depending on digenesis, overprint, and so on. And mercury has some problems. For example, I will show you some of these problems later on, but generally, you know, mercury can be amplified, the peaks, if you have a lot of organic matter, because there is some bacteria which are able just to more or less concentrate mercury. So generally, if you have a lot of organic matter, you can exaggerate, amplify these peaks. If you have charcoals, would be the same. And some minerals also may amplify that. So it's not always so easy. So this mercury stratigraphy, if you want, can be affected by the formation of organic mercury complex, absorption on clays, and it means that sometimes, in order to be sure that you have anomalies, and a lot of geochemical approach is using the same, you have to normalize. And normalize the mercury by, for example, the content in organic carbon, okay? But the problem, sometimes, organic carbon, the organic matter, can be completely oxidized, can be completely destroyed, and the peaks will remain. So the degradation of TOC is also a big problem. But mercury, so is this is a nice paper, very recent paper from Grasby, where mercury is emitted on volcano. It will fall down into, and the better, it fall down directly into the sea and will be trapped into the sediments. This is a good case, in fact. But it's also, mercury can be also produced by wildfire, for example, by more or less the fossil burning of oil, things like that. Can be also enhanced by runoff. If you have more runoff, more reworking of soils enriched mercury, you can create that, and you can have also enhanced organic matter drawdown of mercury. And so anoxic condition, for example, with favor organic matter, so with favor organic the formation of mercury organic complex, which will amplify that signal. So it's not always so easy. Another thing that I can show you here, this is a nice quarry in France. This is Beaujolais. Beaujolais, for people knowing France, this is a place where they are doing an excellent wine. And there is some quarry on the torsion. This torsion anoxic event, we talked about that yesterday. What we did here is more or less to see a little bit what was fate of mercury when you follow always the same level. This is a very thin laminated samples that we samples from very deep black color, means well preservation, good preservation, to white and yellow, meaning a lot of oxidation. And you can see here, for example, that you start at 400 ppb, and in a yellow layer you have zero almost. And the TOC is decreasing also. So here, if you want, and this is very important, you have to think about that. If one time during your studies or your masters, you have to sample a section, be very careful about the preservation of those samples. And here, clearly, in this case, you will not sample the yellow layer, which is completely oxidized by the weathering of actual water, if you want. So all the organic matter is oxidized and gone. And but you will sample that part, and that part will be the real record of your sediments. So these things are quite important. Another examples, this is still from the thoracic anoxic event that we seen yesterday. And this is in Peniche, Portugal, which was located in the term of paleogeography with the beginning of the Jurassic. You see that the Central Atlantic was already open, and this is somewhere into the Tethys Ocean. And here there is clearly, if you take not so much DOC, but there is in some place a lot of charcoals, for example. And charcoals, you can see here, this is a quantity of mercury, will also enhance the quantity of mercury. You have huge peak of charcoals. Even when you normalize the mercury by the TOC, by the charcoals, if you want, you will keep some of these peaks. So it means here that the vegetation is amplifying, is receiving, will get the mercury from the volcanic activity, but will amplify also the peaks. Why? Because in the charcoals you always have a lot of pyrite. This is a sulfur, an iron sulfur, which will also concentrate the mercury. So you have to be a bit careful with the methods. The taking home message here is be careful when you take samples, take fresh samples which are not altered, and have to be very careful of what you are analyzing. You have really to have a look on that. Okay, so what we are doing, this is a project, an ongoing project, and what we decided to look for mercury anomaly from India, very close to the Deccan, to Europe, and even to that place close to Venezuela. This is an ODP site, okay? This is a place, all these points are the section that I have in my office. In fact, we have a lot of samples. Since we accumulate since 30 years almost a huge quantity of section. And this is also the good things. If you like to travel, while studies the KT boundary will help you to discover really a very nice part of the world, from Colombia to Madagascar, for example, without forgetting India, but US and so on. And what we do for some of the section, we were measuring the mercury. So we start by India. I said that mercury generally is released up to the stratosphere, very high into the sky, if you want. And it's not a surprise that there is almost no mercury in the red balls, in fact, because, well, it's not really a distal marker. It would be, mercury will be transported far, far away from the emission source. So I'm not very surprised that there is almost nothing. And here what we did, we measure mercury in different red ball, and there is almost nothing. But if we go a little bit far away, and 1 kilometer far away, in Krishna-Godavari Basin, this is a course for an ONGC, and here you can see that we have a little bit more, and especially close to the KT boundary, there is an increase. It's not so much, from 5 to 25 ppb, but this is an increase. And if you go to Meghalaya section during the Cretaceous is somewhere here, close to Bangladesh. And you can see here, it's a very nice section, probably the best KTB section in India, where you have one of the biggest amounts of iridium, up to 12 ppm here. And you can see that we have a huge peak here. We'll discuss these peaks, but you can see that there is an increase, some peaks at and after. So clearly, Deccan signature here. Since that presentation, we measured also some mercury peak in Anjar, in Gujarat, where you have some peaks, and close to Nagpur also, but there is quite a few peaks. And now I will take you again in Tunisia. This is probably one of the best sections for the world for the uppermost Maastrichtian. That's to say the last 500,000 years of the Cretaceous. And here you have a nice view on the KPG boundary, okay? And this is a KT boundary. And you can see here, this is quite important, I will explain you why. But the KT boundary generally mark a limit between a Mars and something which is a lot more darker, because there is a little bit more organic matter, and there is no carbonate. So it's a boundary here. It's a lithological boundary. And on this lithological boundary, you will have, after the depositification of the sediments, through time, especially actually, a lot of water coming along this layer, which will transform these clay layers. And you can see here there is some gypsum, there is some goethite, and these kind of minerals may also concentrate the mercury. That's why sometimes at KT boundary we have an amplification of this peak. Okay, so let's see this very nice record of Tunisia. And here it's quite interesting. You can see that we have a huge increase with a maximum close to the KT boundary. And here, what we have done, I just switch here because it's more interesting. What we have done here is to have a multidisciplinary studies, including micropaleontology, including stabilized isotopes, oxygen stabilized isotopes on benthic here, mercury anomaly. The mercury, which has been here normalized by TOC in order to avoid this amplification by the presence of organic matter, and very importantly here, cyclostratigraphy. And you can see here that we have this cycle here. This has 21,000 cycles, and we can date, and we base that on the cyclostratigraphy is based on the frequency analysis of the carbonate content, okay, which depend from this cyclostratigraphy. These are orbital parameters depending of more or less the regularity of the orbital of the Earth around the sun, which is varying in a cyclic way, okay? And here, this is quite interesting. We have a very nice signal, not very good here, but well expressed. So you can put age, and you can, after, compare this age with the age, absolute age, that we have found into the Deccan, okay? And after, you can see here, when you start the Deccan activity, you start to have this warming with some cooling event, which are probably linked to sulfur dioxide emission, and you start to get the mercury from volcanic activity with a maximum here, which corresponds to the Polatpur. And Polatpur, I remember, this is this huge formation, 30% of the total lava pipe, which has been emitted in less than 70,000 years. This is really fast. So this is marked almost, as you will see everywhere, by a huge anomaly in mercury, which also is sometimes maximum at the KT boundary. So it's very important because it corresponds to the warming and also to the appearance of what we call disaster opportunist planktonic foraminifera species. This is the one that are more or less occurring when all the other ones are gone, okay? Because you have a lot of stress into the sea, namely probably acidification, as you will see later. So it means that we have a rapid global warming of 3-4 in the deep oceans during that period here. And we have a dominance of high stress disaster fauna during this time. And clearly this has to be linked with the Deccan trap activity. Well, in order to use correctly the mercury, you really have to check if mercury is not linked to the presence of pyrite, organic matter, gypsum, goethite, everything which may amplify this signal and more or less introduce artifact in your curve. It's what we did. I want to go in details in these things, but here you can see that mercury is not really correlated with TOC, so there is no problem. We can use it. And well, if you, well, the correlation of mercury with the normalized mercury is more significant, but this is quite normal. And here, if you take away all the value of TOC which are too weak, generally there is a good correlation. It means that even if you normalize the mercury, you will get the peaks, okay? Meaning that it's a real values. And well, all the samples in that section does not correlate with the clay minerals, so no significant rework terrestrial mercury. Sometimes the correlation is better within goethite, sometimes, especially close to the KT boundary, where I told you that some gypsum and goethite were present, which are related to late diagenetic overprint. And here this is important to make this kind of test, because here you can show that the huge peaks, because here, if you look more or less, you can see that the clay layers, which is these tiny things, contain around 100 ppb of mercury, which is quite a lot. But the gypsum here contain a bigger anomaly, like the goethite here. So it means that these minerals, which are late diagenetic minerals, may also amplify the signal. It's not so important, because it just means one thing, that there was a lot of mercury close to the KT boundary during this time, okay? So the iridium anomaly, for the people who don't know that, is just here. It's a very thin layer. And here in LS, you have some 7 ppb of iridium, which is not bad, which is close to the cave section. And after, what you have to do in order to finish that very nice demonstration, you compare your mercury anomaly here. You can see that this mercury anomaly started 66.4 around in terms of cyclostratigraphy, which correspond quite nicely with the beginning of the Java formation emission, or the one which are more to the north. And this corresponds nicely to this curve. And the most important things here, here's the fact that this huge increase in both mercury and mercury normalized correspond to the last 70 years, 70,000 years, and to the huge polar pore emission, as you can see here. So you have a maximum anomalies just below the KPG, if not at the KPG, which means that you have an acceleration of volcanism emission, 3% of the total volume, suggests really that you have a paroxysmic phase of volcanism due to Deccan very close to the KT boundary. And for me, it's almost impossible to separate what would be the effect of Deccan traps and the meteorite in this case, because it's almost, geologically speaking, in the same time, okay? And very important things here, after if you make a calculation in terms of what polar pore, for example, would release as sulfur dioxide or CO2 emission, it's a lot more than a meteorite. So that's why in a very short period like that, they can make the job without any problem in terms of mass extinction. And this is absolutely very nice data. And we can confirm this data by using other section or a word. For example, LS section, the one that I just showed you, is a quite shallow section. When I say shallow, it's 500 meters deep. Now, let's see a little bit if we go in deeper environment. And this is again the Bidart section in France, the one that I show you with the decreased mass susceptibility, just below the KT boundary. And you can see here that you have a nice mercury peaks, even if you normalize by TOC. So this is not a question of presence of not of organic matter, even if you normalize to phyllosilicate content, to clay content. And here there is another thing which is really important, and this is the work of an Indian colleague, which is more and more known in, for her work on micropaleontology, Janhavi Punekar, and she is professor actually in IIT Mumbai. And Janhavi Punekar is mainly did her PhD at Princeton with Professor Gerta Keller. And what she's looking, this is the fragmentation index of foraminifera. What does it mean? It means, in fact, you have a little bit like in the movie, the Western, the good, the bad, and the ugly. So you have foraminifera which are very nice. They don't have any hole. They are not dissolved. They have a very normal morphology. These are the good. The bad start to have some holes, meaning that there is a starting of dissolution, and the ugly are generally half destroyed. And here, this is more or less these things that you can see here. In green, you have the fragment. These are the ugly one, completely dissolved. And in red, these are more or less one which have some holes, and the good ones. And you can see in both benthic and planktic foraminifera, you have an increase of the fragmentation index. It means what? It means that if there is a fragmentation index, it is because the shell are dissolved and very thin, and so they will break more easily, okay? And this is a measurements of the acidification. And very nicely, you can see that this maximum of acidification corresponds here to this low magnetic susceptibility corresponding also to acidification, to mercury anomaly, and the date is the polar pore emission, okay? So this is quite important because here you have a convergence, a coincidence of several parameters pointing all in the same direction: huge volcanic activity and potential acidification. And another marker, this is the name, these minerals that you can see here. And here these are mapping that you can do with electronic microscope. And these tiny minerals here, if I can read it, yes, the chlorine is here, is full of chlorine. This is a chlorine-rich mineral. The name is a little bit difficult. This is a agakaneite. It's coming from Japan, I guess. And this kind of minerals is found in soils close to volcanoes, okay? And if you find it here, it's another proof of acidification. Gubbio. We have seen Gubbio. This is a place where the Alvarez family, father and son, have discovered for the first time in that layer that you have here the iridium anomaly. And you can see again that in the last zone of the menstruation, you have this low magnetic susceptibility interval, acidification. The first, but low, but you are in deep ocean, so mercury will be clearly less abundant, but a huge peak also is present at the KT boundary, maybe amplified by some diagenetic and things like that. Okay, after that, we can go in Austria. So we are traveling a lot this afternoon. Austria is here, was here during the menstruation. You have Spain, France, and Austria. Austria section is a bit different. Well, this is quite deep with a small turbidite. You know what is a turbidite? What is a turbidite? It's late, but what is a turbidite? Yes, this is some kind of avalanche, submarine avalanche, going through canyon, quite deep, and you have a graded bedding. These are sandstone, mainly. Okay, that's right. So turbidite means that sometimes you are on the slope, quite deep, and well, if you have an earthquakes, for example, but these earthquakes will give rise to this avalanche, which will be deposited, and there is different kind of phases if you are on top of the avalanche and at the end. At the end, you have one of these deep sea fan, which is an accumulation of sand, okay? And these turbidite, well, are quite frequent. But what you can see here, again, we have a lot of mercury. And again, it's always the work of Puneta et al. 2015, what she showed very nicely, that we have again small, let's say, magnetic susceptibility anomaly, but here again a huge increase of the fragment tests, the imperfect tests, so the bad and the ugly foraminifera, which are dominating when you have the maximum of mercury anomaly. So again, it shows that this corresponds and we know that by now, to the Polatpo formation. Okay, and now we end this travel to close to Venezuela, and this is a demilitarized. This is one ODP section, and you take the boat and you do this drill. And here again, what you can see, similar to a lot of this section, you have a nice anomaly starting somewhere 100,000 years before Kitty boundary, maximum at the Kitty boundary, and going on here during this time. Okay? So note also that we have a very nice delta C13 shift, crash in productivity, and again you can see that the bad and the ugly are very, very, very present through that section, corresponding to huge acidification. So if you try to correlate all this section together, this is quite interesting, because you can see that this mercury anomaly are present in all kind of settings. So in shallow settings, in the mid-deep setting, and in the very deep setting. And this is a proof that this is probably linked really to volcanic activity and redistribution from the stratosphere of all this mercury. And you can see here, for example, these are sections from in Spain, in Italy. You always has an increase before, a maximum close to the Kitty boundary. The same in Spain here. The same in Israel here. You can see it. Here there is no anomaly at the Kitty boundary because there is a hiatus, there is no iridium layer. And the same in LS as I presented. So we have a major peaks which mark acceleration of the eruption rate and can be correlated with the Polatpo formation. Okay? So another things, how to be sure that, and these are really an ongoing work, to be sure that these anomalies, are really linked to volcanic activity. And here we can use, again, some geochemistry, which is but we did for the BDAR section where you have this nice anomaly. And here, in fact, you can separate the different origin of mercury by using some isotopes. And there is two kinds of isotopes. Here, this is isotopes, which is these 202 isotopes and 199 isotopes. And you can see that if the mercury is coming from the reworking of the biomass, of the coal, the vegetation, where you can see it, the more or less mass fractionation, what we call MIF, is quite high. You can see you can get value -3 up to 2 or 3. The same for both isotopes. But volcanism, this little v here, has a coefficient which is really, really small. And you can see here that there is, apart these peaks here, but mercury is not very present here, there is no mass fractionation, which is really significant. What does it mean? It means that all this mercury is from volcanic origin, coming from the Deccan. So this is a nice proof, but we need a lot more work to do that. So these mercury things, I just presented these things in the last GSA meeting 2 weeks ago in US. These are the conclusion. Well, the conclusion, exactly what I said. Deccan volcanic may have exceeded many times for the Chicxulub impact, especially the Polatpo, Ambenali, and Malabeshwa formation. Chicxulub impact did not accelerate to amplify Deccan eruption because Polatpo occurred before the KT boundary. And this is a very nice thing that we can correlate our section using mercury anomaly with the Deccan activity, okay? So I really think that major environmental perturbation linked to main Deccan eruption were contemporaneous with the KPG, the Cretaceous Paleogene boundary, and consequently was a major trigger of the mass extinction. And here I can finish that presentation just saying that, well, I really think that in some part, Deccan volcanism, especially Polatpo, which is so close from the KT boundary, put really a huge stress on the biosphere, okay? And in fact, the last perturbation, the meteorite, just terminates the job, if you want. And maybe without the meteorite, nothing would happen, not so sure. Maybe yes, but maybe without the Deccan, for sure, there was no mass extinction too. So you really, it's a good combination, in fact. And this is the only time during Earth history where you have the coincidence, very bad coincidence. It was a very bad day for the dinosaur, in fact, because they got this huge volcanic activity and they got the meteorite on top of that. So here I just want to show you, yes, well, this is on the paper that I was asking you to try to read. I just wanted to this is very nicely done because it's an explanation of all what can happen with volcanic activity, and especially because there is a color code that you cannot read on your Xerox, clearly. That's why I put it here. And you can see here that this Ernst and Ubi did a very nice work about the continental lips, the one responsible for major extinction, by using this color code. You have the direct product of magmatism. You don't have this. You have this in the paper. And all these things is in green, so SO2 emission, some overgas emission, toxic emission, for example, mercury, CO2 emission, and release of other element after erosion, direct products from magmatism. Okay, it's very important. Après, he puts the process here. Depletion, enrichment in bioessential element, dissociation of grass hydrate, increased weathering, and so on. And after, he puts the proxy that you can use, oxygen, there is several proxy, and the kill mechanism. And here you have all the kill mechanism: volcanic darkness, cooling, photosynthetic shutdown for a while, global cooling, global warming, ozone depletion, acid rain, ocean anoxic, ocean acidification, all are these kill mechanism, okay? And they are different if you have a continental lips than an ocean lips. And don't forget to just to remember that continental lips have been a lot more lethal for the biosphere than for the marine one, which were less lethal for the biosphere. And I finished with this very nice picture, which is from Tamil Nadu. Nice Indian elephant, okay? So, tomorrow we will talk about the POTM analog. It will be shorter than that one for sure. Yes, we will. But I'm not finished. I just want to show you something else by now for 10 minutes. And after we will talk about the Anthropocene, and after we'll organize this small debate. So I just remember, if you can read the Nature paper, trying to understand it, and we can discuss a little bit, it would be nice. So now I just want to show you something which is quite good and nice for you if it works. So it's a very nice program, which is I don't want that. Yes, it's exactly what you get when you have a PC. It's why I'm using Mac, because on PC you have any kind of stupid publicity and all these things, but you don't have on a Mac because it's not interesting, economically speaking. There is not enough Mac in the world, but there is many PC. Okay, so it's a nice, if I can, let me see, okay. We will first see. So it's a program, an interactive program. It will take some time maybe. And this interactive program is a way to travel through time. And for example, on that side, I just want to show you how the plate tectonic was evolving through time. And you can see that on that slide you have the time, and you have the temperature and the CO2. And you can stop your cursor where you want, from the Devonian to the KT boundary and so on. You have also the relative sea level. Well, these are numbers. I don't know exactly what are behind all these numbers. Clearly, I'm not sure that you can exactly say that it was minus 120 meters everywhere in the world. Probably not. But it gives you a nice explanation of what happened, if its thing is working. Okay. But I just want to move. Why it doesn't work? Oh, oof. Okay. And now, where is the scale here to enlarge and not enlarge the things on your computer? Syed, when you, I need you. Okay, I just want to show you it works. Can you just, yeah, it's too big. Yeah. 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 Okay. Well, I think. Yes, but we don't see the continent, and we see all these things. It's not very good. Your Wi-Fi is really low, so it's. Oh. This. Okay, so you have to reload that. Sorry. I'm not sure that the demonstration will be so good. But anyway, if you have a computer at home, you can reach that things. You can note website. And here, the good things that you can really, for example, see all the continent moving and all the episodes. And you have the glaciation, but you have also some curve. The evolution of the CO2, yeah, I'm afraid that it will not work. I think you have to go back at midnight here, please. And at midnight, the Wi-Fi, I can tell you, at least in the guest room, is working very well. Nobody is using it. So let's meet us at midnight. And yeah. Oh, maybe. I don't know, it comes. Yes. So it's really nice. You can also see, for example, the actual warming. You have the years from, let's say, the Middle Age up to 3,000 years. And you can see the increasing CO2, the increasing temperature. You can also see the ice melting or forming. You can also see any kind of event, because they put, for example, all the impact event, they put all the extinction event, they put everything, and it's very interactive when it works. But this thing is moving alone. Ooh. No. No way, sorry. Yeah, but it's very difficult. But you can try if you have a computer, a laptop. But try at midnight. There's a lot less people working, and I can tell you, it's super fast. Anyway, just it's a way where you can also put the extinction mass events. And also you can move through time, and you have a graphic where you move more or less the CO2 content, the oxygen content, the temperature. But it will not work, I guess. It's no way. More or less, yes. More and more difficult. Okay, we try 5 minutes, and after we will close the session. You give me also YouTube direction for this one? The YouTube direction, the site. Yes, yeah. Okay, good. What he's doing? Okay, now.
So tomorrow you will be given feedback. If you don't give the feedback, you will not get certificates. Okay? It's mandatory. I will not comment on that.
Yes, this is the election. That's why I said that. This is fast. Oh. Oh. Yeah, but we tried several times. Okay, I think that, well, sorry for that, but just a note, there's a website. As I think it's very interesting and it may help you for your study because there is plenty of things. Yeah, sure. It work on phone, on a smartphone, so you can try. Yeah, we tried yesterday. So, but apparently here it's problematic. No, yeah, here, this one. Yeah. Okay. No, it doesn't work. You can close it, no problem. So see you tomorrow. And so tomorrow we'll talk about the Paleocene thermal maximum, an analog for the next warming. And after we will talk about the Anthropocene. And after you will talk. I hope. No?